Hello, students. If you gaze around where you are sitting, you are surrounded by different types of solids. Pencil, maybe some makeup, some plastic, glass, metal. As a result of this video, you will be able to discuss the forms of solids, identify and compare and contrast the four types of crystalline solids, and apply your understanding of particle attraction to compare and contrast and explain the differences in physical properties of the four types of crystalline solids. So let's dig in. Whenever you have a solid, the most basic way to classify it is either as a crystal or an amorphous solid. Let's talk about crystals first. Crystals have organization. They have the lowest entropy of the three states of matter. They are made of a repeating geometric pattern. For example, sodium chloride, but also sucrose, takes on a basic cubic crystalline shape. If you shake out some salt out of a salt shaker or grab a little pinch of sugar, you'll see, the naked eye can see, the overall crystal that is cubic in shape. That is because the smallest piece of that cube that you can see is called a unit cell. So in the case of sucrose, there's one sucrose molecule that takes on possibly the edges of the cube. Many of these cubes situate together and repeat over and over and over. And eventually we get, thousands and thousands and thousands of the unit cell that we can hold and then see with the naked eye. Now, there are many different shapes of unit cells and many different ways that the particles can actually take on the unit cell position. We don't have to worry about that. We just have to understand that the smallest building block of a crystal is a unit cell, that the unit cells combine to make our overall crystal. And if we're showing the particles in kind of this structural kind of pattern, we call that a crystal lattice. I do believe that this, let's find it here. Here is kind of a breakdown of the terms that I just talked about. The overall crystal structure, crystal lattice, and then unit cell. So this would be an example of a unit cell. This could be an example of a crystal lattice, or this, because it is showing the coordinate system of the different, unit cells coming together. If you would take salt crystals from your salt shaker and crush them with your fingers, you'll actually get smaller and smaller and smaller cubes. And that's because eventually the cube that you can see just from your salt shaker is made of smaller cubes and smaller and smaller. Unfortunately, we wouldn't be able to get it down to one unit cell, but I think from our experience with Legos and so on as kids, we understand how the unit cells come together to make a crystalline solid. The other type of solid is an amorphous solid, and that is one in which the particles have not found an organized place. So for example, carbon in the form of soot. So if you have charcoal, like the black kind of really silky material that's left on a piece of wood maybe that hasn't combusted completely in a fire, or even the black residue if you burn a piece of toast, those carbon atoms are not organized. So one carbon atom might be bonded to this here, and then this maybe over here, and maybe this to here and here, but then this one way over here. There just isn't any repeated order like you see in a crystal. Now there are actually, and some examples of amorphous solids that we interact with every day. So there's plastic, your rubber tires, glass, wax. I wonder how many of us might have a candle burning. So those are some really, really good examples. So before we get into the types of crystals, I want to talk a moment about particle attraction. Because remember, what makes a solid is the particle attraction can finally do what it wants to do and lock the particles in place. The particle attraction is greater than the kinetic energy in the case of the solid state. So if we could review specifically intermolecular forces. Now, intermolecular, that is named so wonderfully because, remember, molecules. We only use the term molecule with substances that are covalently bonded. So we will not have intermolecular forces in ionic. Those are compounds that are made of metals and nonmetals. The metal will be seen first in our formula, of course, or metallic substances. All right, so we just have to make sure that we're just making that correct association. Now, there are 3 different intermolecular forces. Remember, we talked about these in chapter 6. And the best way to classify which type of intermolecular force you have is to know if your molecule is polar or nonpolar. So remember, to tell if a molecule is polar, there is an unequal distribution of electron density. So, water is a great example. Water, remember, is oxygen with 2 lone pairs and then 2 hydrogens. And if we would, just look at this side of the molecule, these lone pairs, as well as a very electronegative element compared to hydrogen, is going to make this side of the molecule partially negative, while this side partially positive. The electrons are spending more time on this side. That will make this molecule polar. Where in the case of hydrogen, well, they're just competing for electrons. They are the same element, so they're going to be pulling equally. The electron density will be distributed equally, and we would not assign one area to be more negative than another. Okay, if your molecule is polar, then you have the dipole-dipole force. So this is present in polar molecules. We could draw a polar molecule as just, an oval, and we know that one side is always partially negative, another side is always partially positive. So when another polar molecule comes in, it's going to align itself. So the positive of one can create this dipole-dipole force with another. And then this will be my negative, and then another one might come in. This will be positive. That'll create another dipole-dipole force. Now, if you are a polar molecule and within your molecule you have hydrogen that is directly bonded to either fluorine or oxygen or nitrogen. So in the case of water, in the case of hydrofluoric acid, this is a polar molecule. This is hydrogen, very low in its electronegativity compared to fluorine. Remember, fluorine has the greatest electronegativity. So this is really going to be an unfair battle for the electrons. The electrons are going to spend so much time around fluorine that almost the electron that hydrogen brings to share in this single bond is stripped away. So this is a very, very strong partial positive and a very strong partial negative. So it's kind of an extreme dipole-dipole. So when another HF comes in, then this is going to create a really strong, now it's still just between the molecules, but it's the strongest intermolecular force. So we could look at the molecule as being a magnet. This would be just a really, really strong magnet, where these are a little bit of weaker magnets. Okay, Lund dispersion forces are present in all molecules, but they are the only intermolecular force with non-polar molecules. Okay, Lund dispersion, if we remember, is just based upon the movement of electrons. We know electrons are moving, really coexisting in a whole, volume at the same time, but we can measure areas where more electrons have collected. Now they're moving, so for a moment where those electrons are going to be a little more negative, and wherever they're not, it's going to be a little more positive. But then the very next moment, those electrons move. And so maybe that negative is over here, and then that'll cause the positive to be there. These are really weak, instantaneous dipoles. These would be the wimpiest magnets. But they do appear, and they do cause, our liquid and solid states with covalent substances. So, as far as strength, Lund dispersion is the weakest, then dipole-dipole, then hydrogen bonding. So substances with hydrogen bonding, we say, have very high particle attraction for each other. Lund dispersion, low particle attraction. Now, Lund dispersion forces can increase with increased molecular weight, because the bigger the molecule, the bigger that cluster of electrons, then it's getting to be a stronger magnet. So Lund dispersion forces can vary in their strength, but usually they're the weakest. Okay, to our types of crystalline solids. Okay, there are 4 types. The first thing you need to be able to do is classify based upon composition. So, what I'd like to do is to fill out part of this chart together. So, our solid types of crystalline solids. Now, I know when we think of a crystal, we think of diamonds and jewelry. But the majority of our world are crystalline on the atomic scale. So if we could jump on Miss Frizzle's school bus and dive into the metal in my wedding ring, or the metal holding up your desk, possibly in your computer, we'd see a crystalline structure. All right, so the types. Ionic, metallic, covalent, molecular, and covalent network. So we should see a similarity in the types of bonding that we talked about, but we have 2 branches of covalent. All right, the first way to diagnose is based upon composition. Composition from the formula. Ionic are made of metals and nonmetals. So for example, sodium chloride, magnesium hydroxide, iron 3 oxide, rust. We could just keep going on and on and on. Aluminum carbonate. Just again, we could just keep going on and on and on and on. All the different ionic compounds we learned how to analyze and name and work with. Metallic, those are going to be metals with other metals, but usually it's atoms of the same metal. Remember, often when we mix different metals, we just get a mixture, not an actual compound. So for example, if you had an iron nail, if you had a piece of copper, or a sample of nickel. All right, covalent molecular. Those are the majority of nonmetals with nonmetals. So water in the solid state, solid carbon dioxide, sucrose. You don't have to know that formula, of course. C12H22O11. So anytime we see nonmetals with nonmetals, the grand majority, 99%, are covalent molecular. So covalent network. Well, this is this very, very, very special, small sampling of compounds that have extraordinary properties. Carbon in the form of graphite, so write in your pencil. Carbon in the form of diamond. Silicon dioxide, quartz. And carbon and silicon compounds. Often silicon carbide and things like that. Now there are more combinations of elements that yield covalent network, but these are the ones that we ask you to be accountable for. So if you were given a formula, could you identify what type of crystalline solid it will take on? So just to take a look, for example, if you're given a sample of mercury in the solid state, well, that's going to be a metallic crystalline solid. And then cobalt-3 fluoride, well, metal, non-metal, okay, that's going to be ionic. Let's say N2O5 in the solid state, okay, just nonmetals, that's going to be covalent molecular because it's not one of these special types. So if you were given carbon in the form of graphite or diamond, silicon dioxide, or any carbon-silicon compounds, covalent network would be it. Okay, so what is the particle attraction? Particle attraction. Well, I can see, ladies and gentlemen, that we're already on this video at 15 minutes. So I'm going to stop here and pick up with the next video. And the next video will compare and contrast, and it's really important to be able to categorize and explain the different types of crystalline solid based upon their particle attraction. That really brings everything together.